Hello and welcome to this tutorial video on what solar efficiency is, why it's important, and how to calculate it correctly for your system. Efficiency is a critical parameter in evaluating the performance and effectiveness of solar panels, which are designed to convert sunlight into usable electrical energy, as well as how it translates through the rest of your system. So, in order to calculate efficiency, we naturally need a formula, which in its most basic form looks like this. Here we can see that efficiency is equal to the output power divided by the input power multiplied by 100 in order to get a percentage value. While I will be explaining a much more in-depth version of this formula later in this video, this basic version will help you to better understand the concept for the time being. Note that the efficiency is denoted by a Greek letter that looks like a lowercase n. However, it's actually pronounced eta or eta, depending on who you speak to. So, in a nutshell, the efficiency of a solar cell is the resulting percentage ratio when calculating the electrical power output in watts in relation to the power of the incident sunlight, also in watts. The input power is better known as the incident solar power, while the output power is known as the Pmax or maximum power output. For example, if a solar cell outputs 200 watts of electrical power and the incident solar power is 1000 watts, the efficiency would be calculated as 200 watts divided by 1000 watts, giving us a decimal value of 0.2. We then multiply 0.2 by 100 to give us an efficiency percentage of 20%. There are 4 key factors that influence solar efficiency, which include the photovoltaic material, the cell architecture and design, the environmental factors, and lastly, the manufacturing quality. Let's break down each of these factors to gain a better understanding of their importance in solar efficiency. In terms of photovoltaic materials, there are a few well-known types currently being used. The silicon makeup of the cells has a huge impact on their efficiency. For example, monocrystalline silicon cells typically have higher efficiency compared to polycrystalline due to their single crystal structure, which provides better electron mobility. An alternative to silicon materials are cadmium telluride and copper indium gallium selenide. These are collectively known as thin film materials. While they offer lower efficiency compared to silicon, they are also less expensive and more flexible, allowing for a wider range of applications. Then there are perovskite and multi-junction cells. These advanced materials have shown potential for high efficiency, but are still under research and development. Make sure to check out this video for more information on these solar cell materials with an in-depth look at the pros and cons of each technology. While the material of a cell heavily impacts its efficiency, its design is also very important. For example, texturing the surface of the cell reduces reflection and increases the absorption of light. Coupled with this, anti-reflective coatings minimize the reflection of sunlight, allowing more light to enter the cell. Then, the passivation layers in solar cells reduce the recombination of electrons and holes, minimizing potential electric current loss. This allows more electrons and holes to contribute to the electric current, thereby increasing the overall efficiency of the solar cell. Since solar cells are exposed to the outdoors, environmental factors must be considered. Solar cell efficiency typically decreases with an increase in temperature. This is due to the increase in intrinsic carrier concentration in the semiconductor material, which leads to higher recombination rates. The intensity and spectrum of sunlight also affect efficiency. Solar cells perform differently under varying light conditions. Then, the angle at which sunlight strikes the solar panel impacts the amount of light absorbed. For this reason, specialized solar trackers can optimize this angle throughout the day. Lastly, both the quality of the materials used as well as the degree of manufacturing influence the efficiency. Higher purity materials result in fewer defects and higher efficiency, while uniformity in cell production ensures consistent performance across the panel. Solar efficiency can be understood at various levels, each reflecting different aspects of how effectively sunlight is converted into electrical energy. These types include cell efficiency, module efficiency, and system efficiency. Cell efficiency is a key metric used to gauge the performance of individual solar cells under standard test conditions. The efficiency of a single solar cell is typically higher than module efficiency because it does not account for losses in wiring, shading, and other real-world factors. The module efficiency is the efficiency of a solar panel or module as a whole, which includes multiple cells. It accounts for practical losses such as interconnection losses, shading, and temperature effects. Module efficiency is therefore slightly lower than cell efficiency, providing a more realistic measure of how the panel performs in real-world conditions. The system efficiency is the overall efficiency of a complete solar power system, including inverters, charge controllers, wire, fuses, connections, batteries, and other components. It is the most comprehensive measure of how effectively the system converts sunlight into usable electrical energy. System efficiency takes into account all potential losses within the entire setup, offering a holistic view of the solar power system's performance. Understanding these different types of efficiency helps in evaluating and optimizing solar energy systems at various scales, from individual cells to entire solar power installations. Accurately measuring and testing the efficiency of solar cells and systems is crucial for assessing their performance and potential, as well as being able to accurately compare the performance between the many panels on the market today. Various standardized conditions and metrics are used to ensure consistency and comparability. Here's an overview of key concepts in efficiency measurement and testing. The standard test conditions, or STC, are defined as an irradiance of 1,000 watts per square meter, a cell temperature of 25 degrees Celsius, and an air mass of 1.5. The STC provides a standardized basis for comparing the efficiency of different solar cells and panels, ensuring that efficiency measurements are consistent and comparable across different manufacturers and technologies. The maximum power point, or MPP, is the point at which the product of current and voltage is maximized. The efficiency of a solar cell or module is calculated at this point as the ratio of electrical power output to the solar power input. The MPP is critical for understanding the peak performance of a solar device. The performance ratio, or PR, is a measure of the quality of a photovoltaic installation. This performance ratio compares the actual output to the theoretical output under ideal conditions. PR accounts for various losses in the system, such as temperature effects, shading, and inefficiencies in the electrical components, providing a realistic indication of system performance. By employing these standardized conditions and metrics, the efficiency of solar cells and systems can be accurately measured and tested, facilitating improvements and optimizations in solar technology. As mentioned earlier, there are various efficiencies that we can measure, including cell efficiency, module efficiency, and system efficiency. While they do overlap in many ways, there are also small differences between them, so let's look at each, starting with the total module's efficiency, as most spec sheets will provide this to us, together with all the variables that we need to calculate this as well. The efficiency of a solar cell is a metric that determines how effectively the cell converts sunlight into electrical energy. A solar module or solar panel contains many of these cells, side by side, which together gives us the total module's efficiency. The formula to calculate this efficiency incorporates several key parameters, including the open circuit voltage, the short circuit current, the fill factor, the irradiance, and the physical area of the module. These parameters are essential for calculating the performance of a solar cell under standard test conditions. Here is the formula for cell and module efficiency, where eta is the efficiency of the solar cell or module. VOC, or the open circuit voltage, represents the maximum voltage the module can produce when not connected to a load. ISC, or the short circuit current, is the current through the solar module when the voltage across the cell is zero. FF, or fill factor, is a measure of the cell's electrical quality, defined as the ratio of the maximum obtainable power to the product of VOC and ISC. The fill factor has its own mini formula using the maximum power point voltage and current, which we will look into shortly as well. L and W are the length and width of the cell, respectively, typically measured in millimeters. These will be used to calculate the total area of the module. The division by 10 to the power of 6 converts the area from square millimeters to square meters for consistency with G. G is the incident solar irradiance, usually taken as 1,000 watts per square meter under standard test conditions, or STC. Lastly, P is the conversion of the output to a percentage value by multiplying it by 100. This formula allows us to calculate the module's efficiency by relating the electrical output parameters to the physical size of the module and the incident sunlight. This helps in optimizing solar array designs for maximum energy conversion efficiency. Great. Let's now enter some values from a JA Solar Module's spec sheet in order to better understand this. I will be using the 425 watt model, highlighted here in red, for this example. Here we can see that it has the following specs under STC. A VOC, or open circuit voltage, of 37.91 volts, an ISC, or short circuit current, of 14.33 amps, VMPP, or maximum power point voltage, of 31.3 volts, an IMPP, or maximum power point current, of 13.58 amps, a physical length of 1762 millimeters and width of 1134 millimeters, and lastly, an irradiance of 1,000 watts per square meter. With these values filled into the equation, we can see that we have everything we need, except for the fill factor. The fill factor represents the quality of the solar cell's electrical characteristics and is defined as the ratio of the maximum obtainable power, or Pmax, to the product of the open circuit voltage and short circuit current. Essentially, the fill factor measures the squareness of the IV curve. This represents how closely the shape of the IV curve approaches an ideal rectangular shape. The spec sheet also provides us with this IV curve, seen on the left. It shows the relationship between the current and voltage at different irradiance levels. The closer the IV curve is to a square, the higher the fill factor, indicating a more efficient solar cell. On the far right is a similar IV curve, except it is based on temperatures. As our equation is based on irradiance, the left IV curve is more relevant to us in this case. Then, just for interest's sake, the middle graph is the power voltage curve. It is not used to determine the fill factor, but rather to show how the power output varies with voltage. As I mentioned earlier, this has its own mini formula which looks like this. We already have the VOC and ISC values, so all we need to do is fill in the maximum power point voltage and current values from the spec sheet. Now, we simply multiply them and then divide it by the product, or multiplied value, of the VOC and ISC. When calculated, the resulting fill factor comes to around 0.782. Great. Now that our formula is complete, we can calculate the rest of it. However, let's do it in stages in order to better understand what's happening. First, let's solve the rest of the numerator, which we can easily do by multiplying the VOC by the ISC and then by the fill factor that we just calculated. When done, we can see that this works out to just over 425 watts. Now, you might or might not be amazed to see that this is in fact the same value as the solar module's 425 watt Pmax output stated on the spec sheet. Therefore, our numerator is in fact the Pmax. Cool, right? With this now solved, we can update our efficiency formula to look like this. Let's now dive into solving the denominator, which includes the area of the module in meters, together with the irradiance. As we already know that the irradiance is 1000, we only need to calculate the area, or A, of the module, which is given to us in millimeters on the spec sheet. So, by simply multiplying the length and the width, we see that it comes to around 1.9 million square millimeters. However, this isn't very user-friendly. To fix this, let's convert it to square meters instead. This conversion is also required in order to keep consistency with G, or the irradiance, which is measured in watts per square meter. To do this, we need to divide it by 1 million. However, entering 1 million into a formula is also messy and prone to errors. A better solution is to express 1 million using scientific notation. This will shorten it within the equation by writing it as 10 to the power of 6 instead. In other words, if you divide by 1 million or 10 to the power of 6, the result will be the same. When doing this, we can see that we get a value of 1.998 square meters, representing the total solar module's area. Great, we can now simply plug this into the denominator of the formula and then multiply it by the 1000 irradiance, resulting in 1998.1. The product of the area and solar irradiance is often referred to as the incident solar power or incident solar energy on a given area. We can therefore conclude that the denominator is in fact the incident solar energy. Inserting this back into our main efficiency formula, we can see that we are almost done. If you've been paying attention, you might have linked the dots and had another light bulb moment. Because if you remember, the very first formula that I showed to you in the beginning of the video is exactly the same as what we have here, where efficiency is the maximum output power divided by the incident solar power. Therefore, another way to express the efficiency formula is by dividing Pmax by A multiplied by G. As we have already solved A multiplied by G, we can simply insert it directly. If we now divide 425 by this value, we get 0.2127. The last step is to change this into a percentage by multiplying it by 100. This gives us a final efficiency value of 21.27%. And right here is the third and final surprise. If we compare this to the spec sheet, we see that it says 21.3%, which is basically 21.27 rounded up. Perfect. You now know the full formula to not only calculate efficiency, but also the Pmax of any solar panel should the spec sheets not provide them, or if you simply want to check that what they are telling you is correct. JA Solar seems to offer very accurate values for their product, which is a good sign. Here is the full formula for reference sake. Okay, great. So now that we know how to calculate the total module's efficiency, what about the efficiency of each cell, and why would we want to do this? Well, the reason we would like to calculate the cell efficiency instead of the total module is because the module includes the metal frame in its dimensions, which doesn't actually form part of any energy generation. Therefore, by ruling this out, we can get an even more accurate efficiency measurement. Fortunately, this is quite simple, as we have done most of the work already. First, we need to see how many cells the module has, as well as what the width and length ratio of these are. The spec sheet and provided module diagram give us clear information on this, stating that there are 6 cells along the width of the module and 18 along its length. This comes to a total of 108 cells, also specified in the spec sheet. Now, in order to calculate the area of a single cell, we simply divide the module's total inner area by 108, thereby excluding the metal frame. Looking closer at the image provided on the spec sheet, we can see that it actually tells us the inner width, which is 1,086 millimeters. Subtracting this from the total module's width of 1,134 millimeters tells us that the total frame thickness is 48 millimeters. Then, to find the width of the frame on a single side, we simply divide this by 2, giving us 24 millimeters. As the diagram does not provide us with the inner length of the panel, we can simply subtract 48 millimeters from the provided total length of 1,762, giving us 1,714 millimeters. Next, we need to find the width and length of an individual cell. To do this, we take the inner width of 1,086 millimeters and divide it by the number of cells, which is 6. This works out to 181 millimeters. We then do the same with our calculated length of 1,714 millimeters, except we are dividing it by 18 cells. This works out to 95.2 millimeters. Now we need the area of each cell, which we can do by multiplying 181 by 95.2, which works out to 17,231.2 millimeters squared. However, as we need this to be in meters in order to multiply it by the solar irradiance of G in our formula, we again divide this by 10 to the power of 6 in order to convert it to meters. Next, we multiply this by 1,000 irradiance, giving us the incident solar power of 17.23 watts. Great, let's finish this off by plugging this into our efficiency formula as the denominator. However, we have one more step to factor in. We cannot use the original 425 watt Pmax as the numerator, as this is for the total module's power output. Instead, to calculate the Pmax of a single cell, we need to divide this by the total number of cells, which in this case is 108. This works out to 3.9 watts per cell. We can now enter this into the efficiency formula's numerator position. Once done, we simply divide it by the incident solar power of 17.23, resulting in 0.22. The last step is to multiply this by 100 in order to get the total value as a percentage of 22.83 efficiency. We can double-check this against the total inner area of the panel by multiplying 1,086 by 1,714, resulting in 1.8 million square millimeters. As before, we divide this by 10 to the power of 6 in order to convert it to meters. We then again multiply it by the irradiance of 1,000. Once done, we can then divide the total Pmax by this value, which, when multiplied by 100, results in a matching efficiency of 22.83%. So, while this is obviously not wildly greater than the total panel's efficiency of 21.27%, which includes the frame, it is slightly more accurate nonetheless. However, realistically, you won't see any real-world differences. But at least you now know how to calculate both. Great, we now know how to calculate both the total solar module and cell efficiency, but what about the total system efficiency? Well, this gets tricky because no two systems are the same. However, in order to do this, you need to factor in the efficiency rating of the inverter, MPPT charge controller, wiring, fuses, and even the battery, together with the solar module. Fortunately, most of these devices will have an efficiency rating on their spec sheets. For example, the Victron 3000 VA inverter has an efficiency of 95%, while the Victron Smart Solar MPPT charge controller has an efficiency rating of 98%. Your cables, connections, and fuses will naturally also have some resistance and therefore lower their efficiency. However, if you oversize, this becomes minimal. Let's assume around 97%. With that in mind, the formula is actually very simple, as we just multiply all these efficiency values together. Now, your battery may or may not show its efficiency rating. However, if the energy is coming from the solar array and being converted straight into AC power by the inverter, this doesn't actually matter. It only matters if the solar energy is stored in the battery before being converted to AC. For simplicity's sake, let's assume it is being converted directly, thereby omitting the battery in the equation. Given the specific efficiencies for the components, the values are as follows. However, in order to accurately calculate the overall system efficiency, we need to multiply the efficiencies of each component. And since percentages cannot be directly multiplied, we convert them to decimal form by dividing each percentage by 100 first. Therefore, module efficiency becomes 0.2127, MPPT efficiency becomes 0.98, inverter efficiency becomes 0.95, and wiring efficiency becomes 0.97. If we input our efficiency values into the formula as decimal values, we get 0.1921 as the output. We then have to convert back to a percentage value by multiplying by 100. With that done, the overall system efficiency, considering the specified efficiencies of the module, MPPT controller, inverter, and wiring, is approximately 19.21%. While this will always be an estimate using this formula, when compared to using high-end measurement tools, it does provide a quick and fairly accurate idea of the solar system's real-world performance. And that brings us to the end of this video. If you've made it this far, I sincerely hope you have enjoyed the content and learned something new. If so, please leave a like and subscribe to support the channel, as well as to get notified of any future videos. Oh, and make sure to check out this video as well. You can also subscribe over here. And this one is pretty cool too. Lastly, don't forget to visit and sign up for a free account at the Blue Power Pro forum.